Good afternoon. Welcome to today's Liftoff webinar. Thank you for joining us. It's brought to you by LIFT, the National Advanced Materials and Manufacturing Innovation Institute. At LIFT, we are the advancing American manufacturing into the future through technology, innovation, and talent development, with a core mission of ensuring the transition, scale up, and fielding of advanced materials and processes that support our nation's economy and security. As a public-private partnership, LIFT unites government, industry, and academia to accelerate the transition of these materials. We are focused on strengthening the defense industrial base, U.S. manufacturing competitiveness, and the national security where resilience, speed, and technological advantage is critical. My name is Christine Longray, Senior Director of Industrial Base Engagement here at LIFT, and I'm excited you're here to join us. For this very important topic, I would like to introduce Leslie Weller from Lockheed Martin, who's going to be sharing her insights on unlocking the secrets of hypersonic flight, materials testing for hypersonics and extreme environments, a critical area of focus as we work together to push the boundaries of what's possible in aerospace and defense. Leslie joined Lockheed Enterprise Operations in 2024, where she oversees and directs the hypersonic material and process tech research portfolio. So Leslie, thank you for joining us today. We really appreciate it and look forward to this very important discussion. The floor is yours, so take it away.
Thank you. Hello, everybody. Thank you for having me, Christine, and the LIFT team. I'm excited to be here today for sure and talk to you a little bit about testing of high temperature materials and materials for hypersonics. Christine mentioned I run the hypersonic M&P Tech IRAD portfolio for Lockheed Martin Corporate. And I also just bring, I guess over 20 years now of materials design, analysis, testing for qualification, testing for properties we need to feed models, and looking forward just to share what I can share with you all today. So we'll go to the next slide. Next slide. I'm on travel this week, so I'm coming to you live from a Residence Inn, if you'll bear with me. And fortunately, the LIFT team has been very flexible and kind about how we're going to go about this today. So I'm still seeing the title slide. One more. Thank you. Okay, so what are we going to talk about today? I want to comment a little on what I intend for this presentation to be versus what it is not.
Excuse me, Leslie. I guess the team can't see our screens right now. So here I'm gonna reshare, and hopefully that should clear things up.
Okay. So many technical challenges this week.
Yeah, hold on. I'm gonna wait until I get confirmation.
Okay.
Okay, I got confirmation, so I think we are good to go.
Great. Thank you. As I was saying, this presentation is distro A, marked for public release. So what it does have is ways to frame the problem. We're going to talk a little bit about the hypersonic challenge, how the types of testing we need to do in order to get to flight of a hypersonic vehicle, how modeling and simulation is really the path there, and that when we're testing, we're trying to generate that data we need so that we can improve our models. And then we will get into some of the different kinds of tests that are available to us that need to be done ahead of deploying a hypersonic vehicle. But what's not in here at this level is really details about loading or you know, a lot of the details, I guess, about what the test facilities do. So I'm hoping to provide a hypersonic testing 101 where you have some places to start and have some references and resources, so you know where to go next to get the details you might need for your test. I also want to just acknowledge there's three folks out there that have done a lot of work in this space, and I use them as references largely throughout this presentation. We'll start with David Glass. He's at NASA Langley, does a ton of materials testing, the NASA Tech Service Tech Reports server. He's published a lot, so we're able to go learn from a lot of the things he's published. And then two other folks in this space, Jeff DeMange and Gerald Russell, also have put together a lot of talks over the years in hypersonic testing. And they are held maybe at an ITAR restricted or and might have a little more detail to them. But they were a big help in putting this presentation together for me. So I do want to comment on this image on the left. I'm sorry, it's on the right. New materials over the years have really been the enabler and continue to be the enabler for new platforms. And this is just a really high level look at that. You know, titanium, we get SR-71, Inconel, we get RX-15, ceramic tiles and TPS and reinforced carbon-carbon. It enabled the orbiter, the space shuttle orbiter. And now we're in this space where CMCs and carbon-carbon and these ultra high temperature materials are the enabler for our hypersonic platforms. So next chart, please. So first, we're going to touch on the hypersonic challenge. You know, why is this so hard? Where does it come from? Hypersonics refer to a vehicle that is going Mach 5 or above. So that's 5 times the speed of sound. And that's extremely high speed, right? So they typically will enter the Earth's atmosphere and encounter the Earth's atmosphere where they have increasing pressure and temperature. And that air pressure, that friction that they experience while going through the Earth's atmosphere, that skin friction is what's generating these extreme temperatures, extreme heat. So you can see temperatures on the surface of the hypersonic system greater than 3,500, greater than 4,000 F. And so we're looking for materials that not only can just exist at those temperatures, but also managing the other complex like aerothermal, structural, chemical reactions that are going to pop up for any material that is trying to keep itself together at extreme temperatures like that. And the bottom line is there is not a single ground test or sounding rocket test, or there's no way to completely mimic what happens in hypersonic flight on the ground. And so with that in mind, we have to piece together and be really intentional with our ground test campaigns as we march towards flight testing for hypersonics. Next chart, please. So I like to put this up here as well to tie together the speed, the resulting temperatures, and the materials that are really available at those temperatures. So this chart on the left is one generated by NASA Glenn Research Center. Along the left side of the chart is Mach number. And our stagnation temperature is typically the temperature at the nose tip of a vehicle. It's going to be the hottest temperature that the vehicle would see, and everything is a factor of your stagnation temperature. Now, in order to generate this chart, I'm sure they made some some assumptions. I'm guessing it's for a spherical shape at the nose. I'd have to dig into the paper a little bit more because I can't remember at the moment. But the point of it is that you can see as you go higher in Mach number along the left side of the chart, you are quickly increasing temperature, which is reported in Rankine here, which I always love. So you want to add about 460 to get to Fahrenheit. And this is essentially saying at, Mach 8, we're at 5,500 degrees F or so. So that's pretty hot. Now, obviously, there are things you do with the shape of the nose, or things you can do with the geometry or the surface characteristics of the material that may pull down from that type of temperature. Like I said, there's some assumptions that went into these calculations, but this is just to give you in the ballpark an eye chart of, okay, if I'm seeing something at Mach 6, I can expect temperatures on the order of 3,000 to 4,000 R. What is that, an F or C or whatever you need? So Mach 5 or above is going to be hypersonic. So we're definitely expecting temperatures on the order of 3,500 plus per, this calculations from this NASA chart. So now if we move to the NASA image on the right, we start to look at our material options. We want something that is strong and low density. That's how we get a number for specific strength over density. So we want that number to be as high as possible. Excuse me. And we want something that can exist at 3,000 to 4,000 degrees F or higher. So when you're looking at this chart, you can start to see the types of materials that are kind of left on the chart in those temperature regimes are our CMCs, our carbon sick, which is in blue, our ACC, which is advanced carbon in yellow. Excuse me one second. Air conditioner at hotels gets me every time. And there's also obviously some ultra high temperature ceramics, which are represented by that gray line along the bottom. But you'll notice that they have very low strength to density ratios, which means you might get a strength that you need, but it's going to be fairly dense. So we want to use those materials in really thin, really small quantities to protect our TPS where we need to. And so the bottom line here is it's extreme speed that leads to that friction on the skin and extreme temperature on the material on the surface, and really pushes us into these limited material options for carbon fiber composites, ceramic matrix composites, and ceramics in general. Next slide, please. I'm just going to grab a quick sip of water while we move.
Leslie, I think there's a couple folks that there's a lot of people seeing it, and there's a couple folks that are not seeing what we're sharing. I might ask those folks to rejoin or refresh. This will be publishable after this event. You will receive a notification and also published on LIFT's website. So we apologize for any technical difficulties the rest of us are having. Apologize. Go ahead, Leslie.
Yeah, thank you for letting me know. I'll keep that in mind. So in this chart, which is titled Hypersonics Path to Flight, there's three major, I guess, things that you have to do. You have to do some modeling and simulation, and then you're going to do some ground testing and hopefully get to flight testing in order to deploy your platform. So on the modeling and simulation size, you're going to start with some preliminary sizing, some geometries, and you need material data there to get that going. So that's going to be your feasibility studies initially, and then as you get to your ground testing, I have some images of various ground testing facilities there that we'll talk about a little later in the presentation. But you will be doing some modeling in sim in order to guide your ground testing campaign. You want to understand your critical components, the places in your modeling in sim where you have the most uncertainty. It could be a joint, it could be um, a really a high temperature of a material that you don't have data for that material at that temperature in that configuration. So with your modeling in sim, you're identifying those spots where you have the most uncertainty, and then you want to kind of lay out your ground test campaign in order to generate data to help you pull down on that uncertainty. And so as you correlate that ground test data, it continues to cycle through and feed your models, and it continues to work towards some semblance of flight testing. We'll talk about it again a little later in the presentation, but there are some opportunities out there these days uh, for materials to get on a flight test, or sensors to be part of a flight test campaign through the MACH-TB program. Um, and so by the time you spend all that money that you will need to spend prepping or getting on a flight test, you want to have done the modeling and simulation and gone through some of your ground test campaign, to ensure that what's going to happen on this flight test to the best of your ability. So all of that data you're generating in your testing is going to continuously feed your models. And, once you have built all the confidence you could in your model, that's when the customer is ready for you to go, sell them a vehicle there. So let's move to the next chart. So talking about modeling and simulation, I broke this out. Why do we test? We have to collect that data for the modeling and sim when it comes to materials. It's often material allowables. It's going to be things like we want to understand a CTE mismatch. We want to understand a surface friction. There's just like the amount of data that we could collect, really, there's no bounds. But sometimes we also want to just demonstrate a capability in a relevant environment. There's nothing like people saying, oh, that's not going to work. Oh, you're going to put that coating on there, and you take it to a high temperature capable, an ArcJet test or a Lemel test or something that gets really, really hot, and it performs because your models told you it would, even though, in theory, maybe it's something out of the box, and getting that data back that said, oh, it survived 3 minutes instead of 30 seconds or whatever it is, that's one of my favorite feelings in this high temperature materials game of, yeah, we got something good here. So sometimes you want to be able to just go to that test facility, prove it out, get the temperature versus time data to kind of go generate more interest, go generate more funding to build up your material capability and test it out further. For analyses for hypersonics, I've listed out some of the things that I've either done personally in my career or seen, that is necessary. You definitely need some initial sizing and design, and oftentimes that comes with TPS thicknesses and temperature capabilities and strengths are involved there. We have to do computational fluid dynamics, where we take our trajectories and apply them to a shape. And from that computational fluid dynamics, we're able to break out expected pressures and temperatures for a given trajectory. Now, a lot of these vehicles are meant to fly multiple trajectories, so you can see how perturbing CFD becomes a really large computational problem, and you're able to pull out maybe some peak load cases and combined load cases, and but that's where you take your trajectory and distill it down into your structural thermal load cases. So then with those loads, you turn to your aerothermal structural analyses, where you're using the applied thermal loads and applied pressures to generate temperatures and stress within a given material. This is where you need a lot of material data, especially with high temperature composites. It really, that test matrix gets really big really quickly, because with composites, you have an orthotropic property set. So the properties are very different in the X, Y, and Z directions, or they can be very different. Oftentimes it's quasi-isotropic, so maybe your X and Y are the same or similar, but your Z is very different. And then you need it over a range of expected temperatures. So you're looking for the shear and in-plane moduli, the conductivities, the coefficients of thermal expansion, the strengths, the fatigue data, and the list kind of can continue to grow as you gain more and more certainty that that is the material you are moving forward with. This is where the rubber meets the road on analysis, and you're generating your margins of safety to prove out that you are ready to fly your system. There's also dynamic analyses that needs to get done. There are dynamic loads like random vibration that a vehicle can experience on the boost phase that we have to account for. And there's dynamic loads in acoustics that can get pretty spicy in hypersonics, and that's due to the 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 loading that the vehicle would experience on the glide phase. It's cruising at Mach 5 plus out there, and so there is some data out there for what acoustic overall sound pressure levels. It's screaming, so to speak, when it is flying that fast. And we have some ways to get after those random acoustic loads. Lastly, we've seen a lot of interest and data come back on weather and particulate impact. The materials often used here are, as mentioned, these materials like a carbon-carbon or a carbon-silicon carbide, and they are 2D laminate carbon fiber systems. Typically, the strengths and moduli and stiffnesses in plane are much higher than what it experiences in the through thickness direction. So it is susceptible to impact, kind of in the way of maybe a space shuttle leading edge was and proved to be, that it can take a pretty small particle impact at a high speed to cause a good amount of damage. So there's interest and tests that can enable you to understand what happens when an aeroshell might go through a dust cloud or a rain cloud, or ways to capture that impact behavior that is helping us to, design with more certainty. So the takeaway here is just there's no perfect analysis. The tools continue to improve for sure, and we have to verify. And the way that we verify our analyses is by measuring data and simulating our systems in realistic scenarios to the best of our ability to feed back to those critical models that we need. Next slide. So here I wanted to talk a little bit about what we call a building block approach. So, say you have a new process for a carbon fiber composite, and this is the thing that's gonna be a game changer, right? Like where do you start? So this image on the left is, it's a classic approach. It's still our approach, right? We start with coupon level testing. We get some feasibility, we get some tension, some compression, maybe some interlaminar properties as well. And we understand or feed the next level up is going to be kind of your sub elements. What are there any, I guess, curved portions or joints or, complex structure that you could make? Is it complex from a processing perspective? Maybe you have a lot of confidence with a flat plate, but that you have like a single or a double radius of curvature type of application that you need to use this material in. What sub element can you make that is just that next level above? And we just keep building off of that. And all of these sub elements and then subcomponents and then full scale components, that data and how you package that data, it should be going back to feed models. It should be being interpreted to be understood for its impact and going back to update a process. It's that data that's going to help you advance your material and continue to grow a capability there. So you want to define clear test objectives throughout the building block approach and have details to your test plan. This is a place where I love the NASA Tech Report Server so much. It's a great resource as a US person. Go see what's been done. And if you're not sure what to do, you can kind of lay something out that mimics what's been done before and see what you can afford from that test matrix to try to go get more money to keep the work going. So next chart, please. So here I highlighted, some of the common data that we're looking for to connect these models and these subcomponents and sub-elements and coupon level testing. I think some of my Greek letters didn't transfer over, but that's okay. So temperature dependent mechanical properties. We need moduli, we need strength, we need Poisson's ratio. These are kind of the baseline building blocks of our aerothermal structural models. It might be that for your application or for your work that you even need it at apply level and not just, it depends on how complex or how detailed, I guess, your model is. And as your project unfolds, that kind of shows itself to you. You keep things as simple as you can until you can't keep it simple anymore, right? But that's where I would start and recommend it, is getting some temperature dependent tension or or shear, just depending on what the type of material or application space is. We also need thermal properties, thermal response, conductivities. Typically in these applications, we're looking for things with higher conductivity. We want to be able to move the heat quickly away from the hot parts of the vehicle. As we move into sub-element and sub-component type tests, we can be looking at combined thermal performance types of testing, where you are getting your sub-element or your sub-component to a temperature that maybe imparts some sort of thermal gradient across it, representative of the application of interest. And then maybe you're adding a pressure load or some sort of moment on the article, so that you're trying to understand how your material reacts to that combination of pressure, of mechanical load at a given temperature, or with some thermal gradient. Thermal gradients are kind of everything in hypersonic flight, right? Like that stagnation temperature at the tip that we talked about earlier in the presentation is very, very hot, and we are using high temperature material to move that heat away as quickly as possible. And when the material is very hot, it expands, and then depending on the CTEs and the strength of the material, we have to understand that behavior, and that's where you can get after that in the sub-elements and the subcomponent level. We also need decomposition properties. There are some cases where you are looking for a shape-stable material, but in most cases, we expect our carbon to ablate away, or we expect, we know the temperature limitation of a silicon carbide or some other ceramic, and we want to be able to model and predict how it's going to behave for a certain time at temperature. And that's something that we can get after through ground testing. You also oftentimes, if you have a new flavor of carbon-carbon or TPS, I guess it doesn't have to be carbon-carbon. If you have a new flavor of TPS, you want to know how its ablation rates compare to materials that have been used before. And that's part of the strategy to sell your material, right? Is this ablates at a lower rate, or it ablates just like this, or or you could learn if it you could just learn a lot from this data, is where I'm going with that. And then we also need those mechanical erosion property sets, and that feeds our impact and weather effects models. And the bottom line here, at the takeaway, just that the design and the modeling, coupled with a detailed ground test campaign, is really what's going to drive down risk in your program and demonstrate the capability. Obviously, generating all this data costs money, right? So we go back to that, in a perfect world, what would you do? But then you want to be identifying the critical pieces, and if you can afford what you can afford, right? So find those partners that can work with you to generate the data you need. Next chart, please. I probably need to speed up. Just a quick touch on allowables. This is, again, kind of a material testing 101 thing. These are the properties that need to be generated on a given program of record for a given material on that program. A basis is typically what is needed for something that is man-rated. In hypersonics, we use B basis, where 10 of 10 specimens fail with a 95% confidence. So as you gain more and more certainty that a given material is going to transition to program, right now that means we need to continue to get data, because you need lots on lots and material lots, not just lots of data. You need material lots that compare to material lots, and lots of samples in order to generate the allowables required for the program. Next chart, please. So those allowables are generally from materials characterization. So this is, again, the part of the presentation where this is not going to be an exhaustive, all-encompassing list of every test facility that we have available to us. So I do apologize if you were on this call and your facility did not make my little map. Please, don't be insulted. Please reach out and let me know what you do. But I wanted to highlight some of the key players in this space. A major one is Kratos SRE in Birmingham, Alabama. Do a lot of high temperature testing and novel material testing. NIAR in Wichita, Kansas is also able to do the required high temperature testing, and they are a space where they are growing capability, it seems, every semester. They get a lot of their students involved directly. So it's a really, really great facility out there. Southwest Research Institute also able to do high temperature material testing and novel material testing, and then CTL out in Cincinnati. So these are just, some places you could look to for kind of that characterization type of test that you might need, and wanted to highlight that here. Next chart. So the next section, we talk about testing in extreme environments. So as opposed to characterization, which is going to be more tensile testing, compressive testing, your classic material property testing, it's this extreme environments part that has to be piecemealed together. There's not one facility, one ground test facility that can do it all. Typically for hypersonics, you have three things you're looking to meet: your pressure, your temperature, and your enthalpy. And kind of the rule of thumb is that you're going to be able to get 2 out of 3. So you have to understand your application space and what's more important. Is it more important to get the pressure and the enthalpy, or is it more important to get the temperature and the pressure, and kind of build your test matrix out from there. We have radiant facilities that we'll talk about, some blowdown tunnels and shock tubes. Our sled test facility, I really only highlight one here. I think there's some others that are coming up online. And then the holy grail of it all is the arc heaters, and we'll talk a little bit about that as well. Next chart. This is another just great resource from, oh God, it's so small on my computer, from NASA, highlighting stagnation temperature, flow duration, and some other key parameters that are in these extreme environment test facilities. And you could see where that line, that delineation is between non-arc jet or arc heated tunnels versus the arc jet tunnels, and how the arc jet tunnels are the ones that get us close to duration, temperature, and the environment, the loads that we need there, which is why they're always full and have a lot of work these days. But there are other facilities that can kind of, like I said, get you 2 of the 3, or demonstrate a capability before you try to get involved with the ArcJet teams. So next chart. Some of the radiant heat facilities to highlight here. There's a few NASA facilities on here. NASA Armstrong Flight Loads Lab. They're able to do combined thermal structural performance. NASA Langley has some facilities for combined thermal performance as well. There's a couple of facilities in Ohio, the Combined Environment Acoustic Lab at Air Force Research Lab, where they are able to impose some of those acoustic loads that we talked about. And there's also, it's called the LEML, the Laser Hardened Materials Evaluation Lab. Can do thermal properties, thermal response, decomposition, and it's all with a very high heated laser. I think they've also introduced some capability for optical materials there that can come in handy. There's a HAPCAT test bed in New York. Sandia National Labs we highlighted here, and also China Lake for combined thermal performance materials testing there. So these are the kinds of places that are going to be able to, maybe with the exception of LEML, that one really is blasting a laser at materials. Some of the others are going to be the kinds of places that can impart a gradient on a structure and then also add a mechanical load and get after some of those critical joints that you might see in a hypersonic structure, and do some unique things there. So lot to be done at these types of labs. Next chart, please. Some of the blowdown, the tunnels, shock tubes, the AEDC, hypervelocity wind tunnel, there's also the propulsion test unit in Tullahoma, a wind tunnel in Tullahoma, and we also highlighted Kubrick up in Buffalo, New York, for combined thermal performance in a tunnel type of environment. And some images there from the good old interweb, just of what that looks like. Lots of big equipment, and that's all I'll say about that. Next chart, please. I wanted to highlight Holloman as well. That is our high-speed test track. So they are out in New Mexico, and I mean, you could see the image there. They are using a sled and a propulsion element to, push things down that sled track at very, very high speed, pretty much right at sea level, right? So the pressures are pretty high, the temperatures get spicy. I guess the temperatures don't get that spicy. I'll come back to that. But what they can do is introduce impact particle clouds of different things, and help us get after, what happens if we go through dust, rain, and what have you. So that's a really powerful test to do out there at Halden. Next chart, please. Ooh, this back end is getting speedy. So highlighting some things about arc jets. So we're simulating heating in a ground test facility with flight-like chemical, physical, and shock flow phenomena. So we're able to get some of that friction shear action on the surface at really high heating. And these are the places where you probably are going to get two of your three needs, your temperature and your pressure, with maybe not quite the right enthalpy, or some combination of that. This chart on the right gives us a sense of, I guess, what some of those simulated environments are for the arc jets listed here. The one at Johnson Space Center and NASA Ames is up in green. Then we have the three arc jets at AEDC listed there as well, and some lines showing the types of trajectories that we would see for various vehicles. The space shuttle being at the top, a maneuverable reentry, a MARV vehicle, scramjet ascent, and an ICBM. So you might have to use your imagination a little bit to figure out where hypersonic boost glide or something would fit along those dotted lines, but another just good reference for what facilities are out there and what capabilities and temperatures, enthalpies they could potentially hit to support your programs. Next chart. Oh, I put another map together. So some of the arc jets highlighted up in NASA Ames, obviously Mountain View. Boeing has an arc jet in St. Louis, Missouri, the Boeing LCAT facility. AEDC in Tullahoma, Tennessee has an arc jet, and NASA Langley has a small one called HIMETS, so you can do some, it's, material samples types of testing there in their small arc jet that they call HIMETS. Next chart, please. I wanted to comment on UCA and some of our university partnerships and facilities, but I didn't have time to, I guess, get permission to use all of their logos and everything. So this chart is a little blah, but the information is good. So if you're not aware, there is an organization called the University Consortium for Applied Hypersonics. It is a collaborative network of universities that are working with government, with industry, with the national labs to do federally funded and federally funded research centers to do research. They host a couple of symposia and forums throughout the year to present on their research, and it is part of the Joint Hypersonic Technology Office, JHTO. My observation about UCA and the universities coming on the scene is we've seen a lot of test facilities come online in the past 5 years, and that has been just wonderful. As a researcher at Lockheed, they're eager to get materials in. If you can accept some risk in your test profile, the universities have been great to work with as they are proving out capabilities of their test facilities. We're able to test materials with them. And some of the facilities I've listed here are folks that we've worked with directly, whether it's CHESS at UIUC, Purdue, the PARI Institute, the University of Texas Arlington has a facility called HiSet that they work in conjunction with. UTK at Knoxville has the University of Tennessee Space Institute, which has a ton of capability, Notre Dame, and there are many more. So this link there brings you to a list of all the university participants, and you can learn more about UCA. I think there are I heard last week something like 1,000 members, student members now. So there's a huge component of it that's workforce development. And it's been I think it's been a really good addition to the the test facilities and kind of breaking down some of um, the things we need at the research level to uh, get answers quickly and have some flexibility while we do research on materials. So next chart, please. So with respect to flight testing, okay, so we've talked a lot about why we test, and we're modeling, and we're modeling our material, then our system and our subsystems. We've done our ground test campaign, and in theory, all of this is working towards a flight test. You can do flight testing at all levels of this building block, though. Uh, if you have material coupons that you are trying to get some extreme environment testing done, or there's a lot of benefit to having like a TRL 7 on a material to show that it was able to survive a flight of some sort. You can design sub-assemblies or subscale critical things, or even a full-scale prototype, uh, and work towards that testing there. Thus far, the representative trajectories are targeted using sounding rockets, where there are a series of them that are part of this program listed at the bottom bullet. Again, I'm guessing many of you on the call have heard of MACH-TB, the multi-service advanced capability hypersonic testbed. So it's a U.S. Department of Defense project to help us increase flight test cadence. They have partnered with commercially available launch services to test materials, components, sensors, and try to generate more flight testing opportunity, so that we can, keep a better cadence. People who are industry part or suppliers of hypersonic materials are often, small companies and folks, universities, folks who don't necessarily have the resources to pull together a full article prototype flight test. So MACH-TB is continuing to grow and generate those opportunities where you can get a material sample, or include your technology in a flight test campaign. So that's been another great addition to the community. Then let's go to the next chart. I also want to comment before I hit the concluding remarks. One way that we're partnering with Lyft, they are working to stand up some testing capabilities for extreme environments, I think an arc jet, in Michigan. So we are working with them to support that and understand what capability that's going to bring to the community and to the table, and look forward to working with them as they gain approval and stand that up. So that'll be another just welcome capability in this test space. I really hope this was interesting and what you hoped for today. I truly believe that advances in thermal protection materials and manufacturing technologies have historically enabled platform capabilities, and they are going to continue to enable our ability to broaden and secure the hypersonic mission space, moving forward against our adversaries. There is not a single ground test to mimic what occurs in hypersonic flight. We have to be intentional with the way we test. We have to understand our application, what data we need, what data we're going after. what we're going to do with that data afterwards. Are we comparing it to something historical, or are we feeding it into a model to then keep going? Are we trying to learn about a process improvement? You know, to be really intentional with how we test and how we go about it, especially considering how much it costs to test. You want to make sure what you're going after is valuable for the money that you're spending. And then measure test data, we need the data to verify the models, because since there's not one ground test, there's not a test that is going to prove out that this is successful in hypersonic flight. Um, we use the model uh, to simulate the flight, and all of that data is going to feed the model that we pull from this intentional test campaign. So it's that materials testing through the building block approach that is going to ensure hypersonic success. That's all I had to share today. I appreciate y'all's time. Apologies again for the technical difficulties. It's been a week all around, I'll tell you. And I'll take any questions. Oh, I said some of these up front. The NASA Tech Report server is just chock full of great information. And then Jeff DeMange and Gerald Russell have given talks similar to this over the years, and I have learned so much from both of them in this space. So wanted to be sure to just give them some shout outs here for what I've learned from them and shared with y'all. Thank you.
Thank you, Leslie. We really appreciate it, and we do apologize for the technical difficulties. This presentation will be shared after this. We are coming up in the hour, so those folks that put questions in the chat, we will distribute those to Leslie. She will answer those, and we'll make sure that we reach out. This was very valuable, lots of information, lots of data, right?
That's great.
It's really important. You shared a lot of valuable resources, I think, which is very important for those that are attending this webinar. We appreciate your membership, your partnership, your insights and expertise. It's very valuable and important to us. So I'd like to thank everybody for joining us today. So thank you, Leslie. Appreciate it. And if everybody will mark their calendar for our next Liftoff webinar, which is September 14th. Thank you, everybody, for joining us, and have a great day. Thank you so much. Bye, Leslie.
Thank you all.
Bye-bye.
Bye, guys. Thank you.
Good time.